Hello guys, welcome back to my YouTube channel. So today I'll be doing an integral that will yield a beautiful mathematical constant. And let's see what that constant is. Let's get to it. So we have an integral, let's call it I, defined as the integral from 0 to infinity of e raised to the negative x power, and in brackets we have 1 over 1 minus e to the negative x minus 1 over x integrated with respect to x, of course. Now looking at the state of whatever is in the bracket, I want to achieve a common denominator. So for that I'm gonna be just cross multiplying everything. So we have e raised to negative x, and when I cross multiply I have x minus this term. So minus 1 minus minus is plus, so plus e to the negative x power divided by the product of the denominator terms. So x times 1 minus e raised to negative x dx. Now I want to pull this part out, just this part. I want to just pull it out of this bracket, and you will see in a minute why. So when I pull it out, I have e raised to negative x over 1 minus e raised to negative x, and then whatever's in the bracket is as it is. So I have x minus 1 plus e raised to negative x all over x. Don't forget the dx. Now I don't know if you see this, but this part, it reminds us of a strange formula we had. It reminds us of the infinite geometric series formula. Why is that? Because say you had an infinite geometric series, say sum from n equals 1 to infinity of a times r to the n minus 1 power. Well then, if the absolute value of the ratio was less than 1, then it converged, then the geometric series converged, and we can directly find the sum of the infinite series by the formula a, which is basically the first term, over 1 minus r. But remember, this is only provided if absolute value of r is less than 1. Otherwise, for all other values of r, the geometric series is going to diverge. So, well, if looking at this formula now, we have a similar expression here, right? Whatever I have bracketed out over here, we have a similar expression, right? So in our case, our a is e raised to negative x, and our common ratio, is e raised to negative x. Now we have to check whether absolute value of r is less than 1. Well, absolute value of e raised to negative x, well, it's always going to be less than 1, because especially on this interval of say x belongs to 1 comma infinity, on this interval always e raised to negative x is going to be decaying, right? Because if you remember the graph of e raised to negative x, it's this decaying function, right? And at x equals 1, if you plug it over here, we have 1 over e. So we have 1 over e. So, and e is approximately 2.71828. So 1 over 2 point something is always going to be less than 1, right? And that was the highest value on this interval of x, from say x, when x ranges from 1 to infinity, 1 over e is the highest value it can get, because after that it is just decaying down and eventually asymptotically approaching 0 as x goes to infinity. So it has a horizontal asymptote at it has a horizontal asymptote basically. You don't need to specify, because horizontal asymptotes are basically when you take the limit as x goes to infinity in this original function. So that is, well, the limit as x tends to infinity of e raised to negative x is going to be 0. I hope you know that, because e raised to a negative infinity is basically having a denominator, a fraction with a denominator that's really, really large. So that's going to be 0. So, well, our criterion is satisfied. So which means we can reverse engineer. We have this term, right? We have we have we have we have the term in the form of the sum formula. So we can now reconstruct, as it were, a geometric series. So let me just clear out this green mess, and let's reconstruct the geometric series. But we cannot ignore certain facts that we know. So we know that a is e raised to negative x, and our common ratio is again e raised to negative x. So let's just construct our geometric series now, because we know that it converges, and we can assume that this is a direct formula for the sum of the geometric series, infinite geometric series. So basically we can write this thing as the sum from, say, n index n equals 1 to infinity of e raised to negative n times x. So you can check for the first term to be a. So if you plug in n equals 1, you're going to have e raised to negative x, and that is truly the first term. And as you keep on increasing n, so when n is 2, you're going to have e raised to negative 2x, which is basically the first term, e raised to x times the common ratio, e raised to x. So you can also check that for e raised to negative 3x when n is 3. So you're going to be having the first term times the common ratio squared. So common ratio raised to n minus 1 power, and n is 3 over here. So 3 minus 1, 2. So it's basically satisfying the general form of an AP, a GP, geometric series. So it satisfies AR raised to n minus 1 form of a typical geometric series when n ranges from, say, 1 to infinity. So basically we have successfully converted this term into a geometric series notation. And in the meantime, everything else in the bracket remains the same. So we have e raised to negative x minus 1 plus x. I just changed the order of this thing, divided by x, and dx as it is. Now we can assume convergence again. Assume convergence. Why? Because then we can interchange these things, right? By assuming convergence. Otherwise you would have required Fubini-Tonelli dominant convergence theorem and all that shit. So I really want to omit that part for now. So we have the sum from n equals 1 to infinity outside, and then the integral inside from 0 to infinity of e raised to negative nx. Since this has an x term, we can't take it outside the integral completely. And we have e raised to negative x minus 1 plus x over x dx. Now I want to free some terms from the bracket. So I'm going to be having the sum from n equals 1 to infinity of the integral from 0 to infinity of Well, I can multiply e raised to negative nx with the first term inside the bracket. So I'll end up with e raised to negative x is basically a constant, but times n plus 1. So you can multiply everything in the bracket and check. So e raised to negative nx, yes, we had that outside, and a minus x, yes, inside, right? So multiplying these exponential terms is basically like adding the powers by properties of exponents. So I hope you saw that. And I'm then going to multiply this e raised to negative nx term with this one. So this will just be e raised to negative nx, because 1 times anything is that anything, and divided by x plus, and then when we multiply e raised to negative nx with this x, the two x's in the numerator and the denominator cancel out, and we can write this as e raised to negative nx, but everything is like common under a common integral, so dx. Well, great. So I think we can definitely split these in terms of two integrals. So let's do that. So we have the sum from n equals 1 to infinity of the integral from 0 to infinity of e raised to negative n plus 1 times x minus e raised to negative nx over x dx, and the second one we have the sum from n equals 1 to infinity of the integral from 0 to infinity of e raised to negative x dx. So let me call this sum integral term I1 and this second sum integral term as I2, and I'm going to be doing them on a separate page, so see you there. So this is basically what we define to be I1, right? So first we need to only focus on this integral over here. Now looking at it, it seems that all our elementary integration techniques are gonna fail. So I'm going to use what's called Frullani's theorem. Let me just use another color. So I'm going to use what's called Frullani's theorem, which, if you know Feynman's integration technique, or otherwise known as the Leibniz rule, it's a special case of that. So special case of Feynman's technique, and you'll see in a minute why. So let me just state Frullani's theorem first. So say we have a function f of x. We have f of x as a function, okay? So if the limit as x goes to infinity of f of x exists, so it should basically not diverge, then the integral from 0 to infinity of f of b of x minus f of a of x all over x is nothing but, say, f of infinity. If you treat infinity as a number, it's actually mathematically incorrect to write infinity, plug in infinity in a function like this, but I'm just doing this for the sake of understanding. So f of infinity minus f of 0 times the natural log of b over a. So basically coefficient over here, b over a. So that's essentially your Frullani's theorem statement. So now how are we going to apply this in our original integral? Well, notice that we have similar functions here with differing coefficients, as it were. So applying it to our case, let's first define what our f of x is gonna be, and then we can check for this first condition. So we had our integral from 0 to infinity of e raised to negative n plus 1 times x minus e raised to negative nx over x dx. So why not define f of x to be e raised to negative x? Because say if I have the limit as x tends to infinity of e raised to negative x, what will that be? It will be a 0, right? So it exists, it doesn't diverge, it exists, it has a real value. And I explained this a moment ago with a green color ink. Now some of you smart viewers might actually ask me, why didn't I take f of x to be e raised to x? Well, that is simply because if you take the limit as x tends to infinity of e raised to x, so as x tends to infinity, as x gets really large, e raised to that really large number is going to be another really large number, right? So it diverges basically, so it doesn't exist, and so the first condition of Fulani's theorem is unsatisfied. So that's why we can't take e raised to x. We have to only take e raised to negative x, because it's going to 0 as x goes to infinity. The limit exists, and we can use Fulani's theorem. So I hope I'm clear over here. Okay, so we established that we can use Fulani's theorem. Now we only need to establish our coefficients b and a. So now looking at this thing, so the coefficients were basically terms that were multiplied with the argument part. So essentially that were multiplied with the x. So what's multiplied with the x? It's this n plus 1 over here, right? So let's define b to be n plus 1 and a to be um, n, right? Just comparing the coefficients again. Well, great. We've established a, b. We know the function f of x. We can just use Fulani's theorem. So by Fulani's theorem, this integral from 0 to infinity of e raised to minus n plus 1 times x minus e raised to negative nx divided by x dx is nothing but f of infinity minus f of 0, everything that will be multiplied with the natural log of b by a. So f of infinity, so basically when you plug in infinity into our f, we get a 0, right? And e raised to 0th power, just write that as it is for now. We know our value of b. What was b? N plus 1, right? N plus 1, and a was n. So yeah, great. Let's simplify. E raised to 0th power, or any number raised to a 0th power, is 1. So 0 minus 1, and the natural log of n plus 1 over n as it is. Okay, so we have a negative outside, and the natural log of n plus 1 over n. So we've basically evaluated our integral now completely. We evaluated our integral completely, but I want you to remember that there was also a summation that was going on with the integral that we evaluated, right? So let's attach the sum to whatever integral we found. So we had the sum from n equals 1 to infinity of the integral of this junk. So basically this part, right? Sum of this part. So now instead of this part, we know that that part is equal to this negative natural log of n plus 1 over n. Fine. Um, Now we can just separate this out a bit. We have sum from n equals 1 to infinity. We can take the negative outside, and by the properties of logs we can write the quotient of the quotient of two arguments as the difference of two separate logs. So we have this basically. Now if you have a lot of experience with series, this might uh, look like a telescoping series. So you're right in that domain. So let's just plug in each value of n and see what happens actually, whether it's telescoping or not, or if we can do something else. So when n is 1, we have the natural log of 2, because 1 plus 1 is 2, and minus the natural log of 1. And then when n is 2, we have a natural log of 3 minus the natural log of 2, and this craziness goes on until we have say the limit as n goes to infinity of natural log of n plus 1 minus the natural log of say n. Because our n was running from 1 to infinity, right? So now notice that all these preceding terms are going to cancel out. We're going to be having a negative natural log of 1, and then this nth term gets cancelled off with this ln of n minus 1 this ln of n minus ln of n minus 1 term, and then this gets cancelled with the previous term. So essentially by the end of all this um, telescoping war, we're going to be only be left with negative natural log of 1, and there's a positive here, so plus the limit as n goes to infinity of the natural log of n plus 1. Now the natural log of 1 is a 0, so by the end of all this we're only going to be left with negative limit as n goes to infinity of the natural log of n plus 1. So that's essentially our I1, right? So I1 was the sum of the integral. So we found out our I1. Now it's time to do our I2. And I promise you, I1 was the hardest part of this entire question. I2 is going to be way easy. So if you remember, I2 was just the sum from n equals 1 to infinity of the integral from 0 to infinity of e raised to negative nx dx. Now this can be integrated easily, very easily actually. So we have the sum from n equals 1 to infinity, and then integrating this with respect to x, we obtain e raised to negative nx divided by negative n, but you have to evaluate that from infinity to 0. So now when you plug in infinity, n equals 1 to infinity, the sum from n equals 1 to infinity, I can take the negative outside. So when you plug in infinity, actually I'll take negative 1 by n outside, be much more convenient to see what's going on. So taking the negative 1 over n outside, I have e raised to negative x that's evaluated from infinity to 0. So that's basically negative 1 over n times the sum from, wait, what am I doing? I just messed up. You can't take the negative 1 over n outside because we have a sum running from n equals 1 to infinity. My bad, I'll just do the corrections here. So you always need to be careful, of not taking the indexing variable out of the sum notation. So I'm just taking the negative outside. So uh, sum from n equals 1 to infinity, and when I plug in infinity over here, so e raised to negative infinity essentially is a 0, then minus this lower limit. So when I plug in 0, I have e raised to 0, which is 1. So 1 over the n that's unchanged in the denominator. So essentially I have the sum from n equals 1 to infinity, and the negatives make a positive. So I have 1 over n, and if I want some perspective, I can plug in n now. I have 1 over n, 1 over 1, sorry, plus 1 over 2, plus 1 over 3 till infinity, right? And what's that? That's the harmonic series to infinity. That's the proper notation for the harmonic series till infinity terms. Well, we found our I1, we found our I2. Let's just recombine everything and see the whole picture. So our original I was just the sum of I1 and I2. So we calculated I1 to be, let me just refer back. So I1 was negative limit as n goes to infinity of the natural log of n plus 1, and I2 was basically the limit as n goes to infinity of let's just use the conventional notation, say from k equals 1 to n of 1 over k. Now let's just rearrange these terms. So I have the limit as n goes to infinity of the sum from k equals 1 to n of 1 over k minus the limit as n approaches infinity of the natural log of n plus 1. Now let's just write this in our conventional harmonic series notation. So the limit as n goes to infinity of the harmonic series of those n terms minus. Now I want to remind you of a fact, or we can just do a simple variable substitution. So okay, instead of a variable substitution, I would like to show you that if you have the limit as a variable, random variable, say b, approaches infinity of say b, that is equal to, in the limit as b approaches infinity, b plus 1, because if you say sort of plug in infinity, you have infinity, and then when you plug in infinity over here, you have infinity plus 1. So a very big number plus small number such as 1 is still a very big number, namely infinity, right? So the meaning of both of these things is the same as long as you have the limit as b tends to infinity. Now we can take the natural log on both sides. So the natural log of the limit is the limit of the natural log, so because they're continuous. So the limit as b approaches infinity of the natural log of b is the same thing as the limit as b approaches infinity of the natural log of b plus 1. So we can actually use this great fact to say that this thing over here actually equals the limit as n approaches infinity of the natural log of n, right? Using this identity, if you want to call it, this fact rather. So instead of the natural log of n plus 1, we can write the limit as n goes to infinity of the natural log of n. Finally, we have the limit as n approaches infinity of harmonic series of n terms minus the natural log of n. We basically took a common limit here. Now this, by definition, you might have already foreseen it, is the Euler Mascheroni constant. Is the Euler Mascheroni constant, or if you want to write it in terms of digammas, is a negative digamma of 1, because a digamma of 1 is negative Euler Mascheroni constant. So it was a beautiful mathematical constant that we obtained by doing a crazy integral and using Frullani's theorem. So in conclusion, what did we do today? Today we had an integral that was defined as the integral from 0 to infinity of e raised to negative x, and in bracket we had 1 over 1 minus e raised to the negative x power minus 1 over x dx, and that evaluated to, surprisingly, the limit as n approaches infinity of the harmonic series of n terms minus the natural log of n taken under a common limit. And this, you can say, by definition equaled the Euler Mascheroni constant. So directly this is equal to the Euler Mascheroni constant. I mean, who would have guessed? But that's how math works, right? It just gives beautiful results for things that don't look anything like the final result. So I really hope you enjoyed this video. Please like, share and subscribe. Recommend my channel to others, and if you have any doubts, I'm always approachable in the comment section. So stay in, stay safe, peace out, have a great day.